Okay, if we look at this problem, it's nice to see the same correct answer all the way across the board. The pH is 3.43. We set up our ice chart, 0.010 molar for the initial concentration, zeros for the H plus and A minus. Everything changes by X. The HA goes down, the H plus and A minus go up. And at equilibrium, we have 0.010 minus X for HA, X and X for H plus and A minus. Our Ka is 1.4 times 10 to the negative fifth, so we can assume X is small. So then we set up our Ka 1.4 times 10 to the negative fifth is equal to X squared divided by 0.010 molar. And this gives us an X value. X is representing the hydrogen ion concentration, 3.7 times 10 to the negative fourth molar. So the pH is 3.43. We have two sig figs in the number, so we get 2 digits to the right of the decimal in the pH. Now, when we have a situation when Ka is big, and I'm saying bigger than 10 to the negative third, 10 to the negative fifth, you're always pretty good. Sometimes you can get away with a Ka of 10 to the negative third, assuming X is small, if your starting concentration is high enough and if it doesn't go out a whole bunch of decimal places. If it's like 0.50 and you're only going out 2 decimal places, you can usually get away with it. But when Ka is not small, then we have to do a quadratic. So we're going to do one just for kicks, just to show you how this is done. So let's calculate the hydrogen ion concentration in a 0.00100 molar of some weak acid, which I'll call HA. Doesn't matter what it is. And the Ka is 1 times 10 to the negative fourth, and this is kind of a small concentration. So we do it the same way. HA is in equilibrium with H plus plus A minus. We set up our ice chart. My initial is 0.0010 molar, 0 for H plus and 0 for A minus. I'll go down by X and up by X for the two products. Then I have 0.0010 minus X, X, and X. Now, in this case, we cannot assume that X is small when we're subtracting, so we have to deal with it.
Why can't we assume that?
Because this is not really super small. We only have one significant digit here, and we have kind of a low starting concentration.
So it's less than 10 to the negative third?
But not 10 to the negative fifth. And this is small. Okay? Usually, if it's 10 to the negative third and the starting concentration is like 0.10, but here we've got 2 leading zeros. So 10 to the fourth is negative fourth is kind of iffy, and when you combine that with a smaller starting concentration, you will see that it is significant. So now we only have one sig fig in our K value. 1 times 10 to the negative fourth is equal to H plus X times A minus X divided by HA 0.0010 minus X. So now we're going to rearrange 1 times 10 to the negative fourth times 0.0010 minus X is equal to X squared. So rearranging this into the classic form for the quadratic, well, I guess multiplying across first, we get 0.0010 times 10 to the negative fourth minus 1 times 10 to the negative fourth X is equal to X squared. And now we get to rearranging 0 is equal to X squared plus 0.0001X minus 1 times 10 to the negative seventh. So we think of this as 0 is equal to AX squared plus BX plus C. So we identify our variables. A is equal to 1, B is 0.0001, and C is negative 1 times 10 to the negative seventh.
How did you get negative 7?
I multiplied something.
No.
Okay. You see it?
Yeah.
You get it from multiplying out. So we know that x is equal to minus b, negative 0.0001, plus or minus. Now, when you do the quadratic, you get two roots, but only one of them makes sense in chemistry because you can't have a negative concentration. So it'll be plus or minus the square root of, because we know x is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. So it's equal to b squared, which is 1 times 10 to the negative 8th, minus 4 times a, which is 1, times c, negative 1 times 10 to the negative 7th, all divided by 2. And when we solve this, we get x representing the hydrogen ion concentration. We only get one sig fig, 0.0002. So then my pH is equal to 3.6. And if you look at this, if we are subtracting 0.0010 minus 0.0002, it does become significant at this point because we had such a low concentration to start. So that's an example. If we need to do a quadratic, we can. We're going to go ahead and take our break. We're a little bit late on the break, and then we'll come back and have you work this one. Just work it at your seats. I want to make sure everyone knows how to do a quadratic, and if there are any problems, I'll come around and help you.